In section 8.2, which is area of a surface of revolution, we want to define the area of a surface of revolution in such a way that it actually corresponds or matches our intuition. So for example, if we take a cylinder, forgive my drawing, but if we take a cylinder whose base radius is r, it's r, and its height, we can make a better h than that, is h, and if we cut it along this dotted line here, then what do we get? We get a rectangle here whose length is 2 pi r and whose width is h. Okay, so the area here is just 2 pi r h. Now what we want to do in this section is we want to take the same idea that we just discussed, and we want to look at surfaces of revolution. So in other words, we want to look at maybe an object that has the resulting surface, and we want to look at a particular part of this, and for example, we'll take the band that's created here, so in this particular part, and we want to use that to help us find our surface area. So we'll use an approximating band to help us find our surface area. But notice here we also take into account the length of the curve. This brings us to the following. First, case 1, we have that the rotation about the x-axis for a function y equals f of x and x between a and b, we have the surface areas given by the following. It's the integral from a to b of 2 pi y times the square root of 1 plus dy dx quantity squared times dx. Note here that we're just taking into consideration the arc length from the previous section. Case 2 is suppose we want to rotate a given function about the x-axis, where our given function is x equals g of y, and y is between c and d. The surface area here would then be the integral from c to d of 2 pi y times the square root of 1 plus dx dy quantity squared dy. Note here, we're integrating with respect to y. In case 3, if we take a given curve and we rotate it about the y-axis, then our surface area is going to be the integral of 2 pi x ds, where either ds is going to be the square root of 1 plus dy dx quantity squared times dx, or ds can be the square root of 1 plus dx dy squared dy. Now let's go through an example. Okay, now let's find the surface area of the surface obtained by rotating y equals the square root of 4 minus x squared, where x is between negative 1 and 1, about the x-axis. Okay, so let's recall that the surface area, since we're in case 1, the surface area is the integral from a to b of 2 pi y times the square root of 1 plus, instead of writing dy dx, I'm going to write f prime of x. We're going to square that, and we're going to multiply that times dx. Okay, so in our particular case, what is f prime? Let's make a better f. F prime of x. Okay, well, it's 1/2, not 7, it's 1/2 times 4 minus x squared to the negative 1/2, but we have to use a chain rule, so we get times negative 2x, and we simplify that, we get negative x over the square root of 4, that's a 4 here, just erase that, over the square root of 4 minus x squared. Okay? Now, we use this in our formula for this point here. And we know that y is the square root of 4 minus x squared, so we substitute that in for y here. So now we can say that s is equal to the integral from -1 to 1 of 2 pi. Our y is the square root of 4 minus x squared, that's 2, x squared times the square root of 1 plus x squared over 4 minus x squared. Now remember, we're getting this because we had to square f prime of x. Okay? But all of that dx. Okay? Now this is equal to the integral from -1 to 1 of 2 pi times the square root of 4 minus x squared times the square root of 4. We're going to find a common denominator here, which is 4 minus x squared. So that gives us, in our numerator, 4 minus x squared plus x squared, that's squared, all over 4 minus x squared, okay, dx. And let's try to make this smaller again. Good. Now this is equal to, you can write, that's equal to the integral from -1 to 1 of 2 pi times the square root of 4 minus x squared times the square root of what? 4 over 4 minus x squared, all of that dx. Okay, now we're smooth sailing. Let's move this to the next slide. Before we move, let's make a note. Here you have 2 pi, right, which is constant. So we can move this outside. And we have the square root of 4 here over 4 minus x squared. Now remember that the square root of a fraction is just the square root of the numerator over the square root of the denominator. Well, the square root of 4 is just 2, so we're going to move that 2 on the outside as well. And when we do that, we get the following. That is now the 4 pi, well, right with a pen, it's 4 pi times the integral from -1 to 1 of the square root of 4 minus x squared times 1 over the square root of 4 minus x squared, all of that, times dx. Well, if we look here, we can cancel out the square root of the 4 minus x squareds. So we're now just integrating from -1 to 1 of dx. And this is a -1 here. From -1 to 1 of dx. So this is just equal to 4 pi. The antiderivative of 1 is just x. We're evaluating from -1 to 1. And that's equal to 4 pi times 1 minus -1. And this will give us 8 pi. And that's it. Okay, so now you should work through some more examples. That concludes area of a surface of revolution.